Let's continue with our discussion of sequences. The absolute value theorem for the sequence AN. If the limit as n approaches infinity of the absolute value of your sequence equals 0, then the limit of your sequence without absolute values will also equal 0. This is a really good theorem to apply if you want to check out an alternating sequence where you have like a -1 to an n term where every other term will be negative. All the other ones will be positive in between. For example, let's actually look at the sequence -1 to the n times 1 over n factorial. As a quick reminder, n factorial, you start with 1 and you count upwards until you reach whatever factorial you have. That's 1 times 2 times 3, and you keep going until you hit your target number. For example, 4 factorial, 1 times 2 times 3 times 4, that's 24. 0 factorial is defined as 1, so I want to make a quick mention of that here. Now let's get back to our sequence. We're going to use the absolute value theorem to show that this sequence converges, and because it converges, we'll find its limit. When you take the absolute value of an alternating term, all this term does is jump back and forth from negative to positive. When n is odd, the term is negative. When n is even, the term is positive. When you take the absolute value, you remove that sign alternator, and that gets us down to the limit as n approaches infinity of 1 over n factorial. Well, the larger n grows, the smaller this fraction gets overall, and that limit is actually 0. Therefore, we can say by absolute value theorem that this sequence does converge to 0. Another example, let's find a sequence whose first 5 terms are 2, 4 over 3, 8 over 5, 16 over 7, and 32 over 9. Some of these take quite a bit of work. Don't forget this 2, you can treat it as 2 over 1. All of these top numbers, the numerator values, seem to be powers of 2. 2 to the first, 2 squared, 2 to the third, 2 to the fourth, 2 to the fifth. Our sequences climb by natural numbers, positive integers. So our numerator, because it's powers of 2, I know that I can write it as 2 to the n. The denominator is a little bit harder to look at and try to find its term, n term representative. Now this first one again is over 1. So we have 1, 3, 5, 7, and 9. Those are all consecutive odds, and they're all positive. So 1, 3, and remember this is our first term, 3 is our second term, 5 is our third term. So if you use 2n minus 1, the first term, 2 times 1 minus 1, gives you that unwritten 1 for denominator. The second term, 2 times 2 minus 1 is 3. Third term, 2 times 3 minus 1, that's 5. And we have discovered the pattern. Our numerator is powers of 2. Our denominator is consecutive odds. And so that's how we would define the sequence where this is the first, these are the first 5 terms. Now, once you've discovered the nth term of a sequence, you can take the limit of your nth term. Now, this case, it's going to be infinity. This is going to be a divergent sequence. When you let n get really large, the numerator goes to infinity, but the denominator does too. Applying L'Hopital's rule, this derivative of the numerator is 2 to the n times natural log of 2 over the denominator has a derivative of just 2. Since the numerator contains a variable after the derivative, but the denominator becomes constant, this sequence will really grow and grow fast. A sequence AN is monotonic when its terms are either non-increasing or non-decreasing. Excuse me. This sequence we've looked at before, 3 plus negative 1 to the n. For convenience, I've written out the first 4 terms. When n is 1, you have 3 minus 1, that's 2. When n is 2, this becomes positive 1, 3 plus 1 is 4. It turns out this sequence just bounces back and forth from 2 to 4 to 2 to 4. Now I'm going to casually mention some vocab along the way. When n is 1, a sub 1 is 2. When n is 2, a sub 2 is 4. But then you drop back down to 2, back up to 4, alternating 2s and 4s. This sequence is in fact bounded above by 4, bounded below by 2, but it's not monotonic because there's increase followed by decrease followed by increase. Monotonic, you either want it all to decrease the whole time or increase the whole time. Let's look at a second sequence. Let's look at b sub n defined as 2 times n over 1 plus n. If n equals 1, you get 2 over 2, which is 1. If b sub 2, that's 4 over 3 for 4/3. b sub 3 is 6 over 4, which reduces to 3/2. And then finally, b sub 4 is 8 over 5, 8/5. These terms consistently increase or get larger. This is what you look for monotonic. There's only one direction. Either the terms increase the whole way or decrease the whole way. If I were to take the limit of this sequenced nth term, the limit of 2n over 1 plus n, I'm going to get 2. It turns out that this sequence is monotonic and bounded above by 2, so we have a convergent sequence bounded above by 2. And that leads us into the theorem for bounded monotonic sequences. If a sequence AN is bounded and monotonic, then it converges. If your sequence is decreasing and bounded below, it's convergent. If it's increasing and bounded above, then it's also convergent. And that's really what you look for in the long run, is increasing and capped above, decreasing and capped or bounded below. This sequence is also bounded below by 1 because that's the smallest value it ever takes on. But as far as convergence goes, you want the direction it's heading to be monotonic and have a ceiling if it's increasing. Another example, a sequence Bn defined as n squared over n plus 1. I'm going to go ahead and take the limit. Using L'Hopital's, if n goes to infinity, we have infinity over infinity. Taking the derivative, you get 2n. Taking the derivative, you get 1. N on top gets larger and larger. Denominator is fixed. So this limit goes to infinity. And I put a little note out here that L'Hopital's is how I discovered that. Writing out the first 4 terms of this sequence, b sub 1 is a half. That's 1 squared over 2. B sub 2, that's 4 over 3. B sub 3 is 9 over 4. And finally, B sub 4 is 16 over 5. Let's plot these values. This is for n 1, 2, 3, and 4. So b sub 1 was a half. B sub 2 was 4/3, which is 1 1/3. B sub 3 is 9/4, that's 2 1/4. And finally, B sub 4 was 16/5, which is 3 1/5. Monotonic, because the values increase all the time, increases, but because this limit is not finite, it is not bounded above and therefore divergent. See the difference? This time we're increasing, but there's no cap on it. Increases without an upper bound. And then finally, another example would be the sequence a sub n defined as just 1 over n. A sub 1 is 1, a sub 2 is a half, a sub 3 is 1/3, and finally a sub 4 is 1/4. These values consistently decrease. A sub n is monotonic, and because it's decreasing, every term gets smaller and smaller. And it's also bounded below. Now, decreasing with a bottom or lower bound will tell you that the sequence converges. The limit of 1 over n is 0. So the farther you stretch this sequence out, you'll get a 5th, a 6th, a 7th. Eventually you run into 1 over 1,000,000, 1 over 5,000,000. That sequence converges because it's monotonic, decreasing, and bounded below. Let me know if you have questions over any of the sequence parts, and reach out by phone or email, swing by the office, or just ask in class, and I'll do my best to help you out.